Okay, so we're going to do a little bit of review on some of the things that are necessary for these types of word questions. Then we'll talk about exactly how to do these. When we talk about optimization, we're talking about questions that ask you to find the max or min of some sort of situation. So like minimizing the cost of a certain product. Did you just, no, Jackson was here. I don't know why I thought you just walked in. All right, I must have woken up a little bit too late today. Maximizing profit, right? That's a type of max or min question. And not just min or max, but like of cost, but transportation time and the min or max of a container's dimensions so we can fit something in it. So anything that asks you for the minimum or maximum something, that's a type of question that we put under the whole blanket of optimization. Okay. Now, before we even talk about how to solve these, let's try to go through how we're going to find the min or max of any function on either a closed interval or an open interval or somewhere where we don't have any boundaries. Okay, so let's do a little bit of review here. Let's say we have a function f, okay, and we want to find the absolute minimum and absolute maximum on a closed interval. Does anyone remember the method that we use for that, Michael?
Find the critical values and then you plug in the interval points or the values.
Perfect, right? I think we had a name for it. It was called like the closed interval method, which is what Michael's describing here. So let's just write out what this closed interval method is. Okay, so closed interval method. And Michael said, okay, first we have to find the critical values, right? That's kind of what we do when we're looking for absolute mins or absolute maxes. So find CVs. Okay. You said we're going to plug in the critical values into the function. So plug CVs into F. Okay. And then Michael said we also have to plug in the endpoints because the endpoints are also places where we can have a minimum or maximum, right? So plug in endpoints. And then we basically look for the highest and lowest out of all the numbers that we plug in, right? So we look for the biggest and the smallest number. Okay. Now, what does the closed interval give us? Does it give us the absolute max or min, or does it give us the relative max or min?
It's absolute.
It's the absolute max, right? It's literally like the highest point and the lowest point on the graph. So this gives us the absolute max and min. All right, and I think I gotta get Daniel his notes here. Hey, nice. Sounds like I planned that out or something. All right. So that was the closed interval method. So when we're on a closed interval, like 2 to 3, and we're looking for the highest and lowest, that's what we do. Okay. Now, if I'm looking for maxes or mins on like an open interval, so like if we use parentheses, or usually the open interval that we use is like all real numbers, right? So we have a polynomial and we're looking for the max and the min on the real numbers. What did we do there to find maxes or mins? There are actually 2 ways we could have went about it. They have very specific names and they're like numbered. And they have to do with derivatives.
Oh, the first and second.
Yeah, the first and second derivative test, right? So we have kind of 2 options here. And this is how did I do this? I don't know how I did this, but I planned out. Oh my goodness. All right, so we have the first derivative test. Okay, and can someone remind me like what we do for the first derivative test?
Put it on a number line and then you plug in numbers that are before and after the critical value that you're looking for. And if it's like it's positive and negative, and it goes from positive to negative to max and then negative to positive to min.
Perfect. That's literally exactly what I was looking for. So basically we have the number line, right? And we plug our critical numbers on the number line. So like our first CV, maybe our second CV, and we make little areas to test values. And what we're plugging in is numbers around the critical value. And I think Sam said we're plugging it into the first derivative, right? Okay, and basically that tells us if we're increasing or decreasing, right? And that kind of tells us if we have a minimum or a maximum, if we go from like increasing to decreasing or decreasing to increasing. So that's kind of like the big test that took a lot of time plugging in numbers, but it was really useful to figure out if we had a min or max there, okay? Then we had the second derivative test, okay, which is kind of the same. We look for critical values, right? So we plug critical values, and it's called the second derivative test. So we're probably plugging things into the second derivative, right? Now, when we plug this in and we get something positive, what does that tell us about a min or max? It's a min, right? It's kind of counterintuitive. Like I always think if something's positive, it has to be a max, but it actually means the opposite. When it's negative, it's a max. And what happens when we get 0? Yeah, you got to do more work, and more work just means go back to the first derivative test and do the increasing, decreasing, right? So the second derivative kind of fails, so you have to go to the first derivative test. Okay, so there's 2 ways of figuring out if we have a max or min on an open interval. Basically, like if you have a polynomial and you wanted to find maxes or mins and you didn't have like a closed interval for that. Okay, what does the first and second derivative find? Do they find absolute or local mins or maxes? Local, right? So this gives us the local min or max. Okay. So when we do these questions that are word problems and we're looking for maxes or mins, sometimes the question is going to give us a closed interval. So we're going to have like a set value or set number of things that can go into a function. And that gives us a way to solve it. We'll use the closed interval method for that. And sometimes we're going to be given a situation where we're looking at just a function on the real numbers or maybe an open interval. In that case, we're going to use the first or second derivative test to figure out maxes or mins. Okay, so there's 2 types of questions that we can get asked here. Okay, now I would say the hardest part about these optimization questions are going about it in like a systematic way, which is why I kind of have steps for this. Okay, so when we have a word problem, first thing you're going to do is just draw a diagram, right? Usually that kind of helps us. Make sure that we have notation, know what the symbols mean when we write out our questions. We have to create an equation, okay, because that's what we're trying to take the derivative of. And I'm going to write down here to make sure our equation only has one independent variable. So there's no like, it's only X in our equation. It's not like X and Y or X, Y, and Z, okay? That might make more sense when we do an actual example, okay? Number 4, we're gonna think about our equation in context with a question, and we're gonna think about if there's a domain to our function, okay? So what values make sense for the question? If that doesn't make sense, we'll do an example and it'll make a lot more sense there. And then step 5 is to either use the closed interval method or one of our derivative tests to figure out if we have an absolute max, local max in our question. Okay, and we'll talk about why local maxes even matter here. All right, now if that made any sense, congratulations. We're actually going to go do an example and see what these steps actually turn out to be. Yep. This is a very classic optimization question. We have a farmer. He has a bunch of fencing. He actually has 2,400 feet of it. And he wants to create a fence to create like a rectangular field, okay? Now this field borders a straight river. So along the river, he actually doesn't want to put fencing because it doesn't really matter there. And we want to figure out the dimensions of the field, so length and width, that has the largest area, right? So we want the biggest area possible with this amount of fencing. Okay, So let's draw a picture, see what happens. So step one is drawing our diagram. Okay, is that rain? No, that's a cart. All right, so we got this fence and we're bordering a river, right? So I'm gonna draw the river out here. This is like my favorite part of this class, so just let me have my fun here. Let's have our little river here. All right, and then we want to put our fence around the river. Okay, so our fence is going to kind of look like this. It's going to be rectangular, but we're not going to have any fencing next to the river because that wouldn't make any sense. Okay. I don't know. What do you think I should label like the lengths of the fence?
X and Y.
I don't really like X and Y. That's
LW.
L and W. I like L and W. That's fine. I don't know why I asked. X and Y would be fine. Let's do L and W. Okay, L can be the length and W can be the width. Sorry, Jude. Okay. And we don't have any length on the bottom because there's no fence on the bottom because that's where the river is. Okay. Step two is labeling what we're going to make our variables equal to. So I guess L really means the length. W definitely means the width. Okay, and we want to figure out something about the area. Area is usually A, right? I would ask, but I know Jude's going to be like, I don't know, Z for the area. So let's just make A equal to the area. All right. Hey, I could draw you in the picture. I haven't done that yet, so. I did. I here we go. There you go. There you go. I think it looks a little, I don't think it looks like, here we go. Well, that just looks worse. I'll give you a haircut. There we go. I think that looks a little better, doesn't it?
We can start all that on our test.
Yes, if you draw this on your test, I will not give you any extra credit, but I will laugh at it. Then I'm just gonna get some weird drawings on my test if I tell you extra credit. I think that's good enough. We're fencing in Jude, so we can't escape the fence. All right. Let's do step three. All right, step three says we need to create an equation, right? So we need to find an equation to represent the area of something. Any ideas on an equation we can use for the area?
I was just gonna say, if we'll present fence, can we do like 2400 equals 2W plus?
Okay, good. So let me write out what Michael said. So Michael said, we can do this. 2400 is the length of the fence. So that's how much fencing we have. And you said that it is, what do you say the equation was?
2W plus L.
Okay, and how did you create that equation?
2400 fence.
Yeah, right. So, oh, yeah. So there's two W's and there's one L, right? And there's no second L there. So that's why there's only one L and there's two W's because the fencing kind of goes on both sides. Okay. So this actually represents kind of the perimeter of the fence, right? So this, I'm going to call this equation one. Okay. All right, but that doesn't give us anything about the area, right? We want to figure out something about the area. We want A in an equation. So can someone give me an equation to represent the area of the fence? Yeah, perfect. Length times width, or X times Y, right? So A equals length times width, and that's our equation number 2. Okay. Now, we want to maximize the dimensions that has the largest area. So we want to maximize the area of something. So which function are we really trying to like maximize? What are we trying to take the derivative of?
Area.
The area, right? Because we want to find what has the largest area. that's the thing we want to find, or what we want to discover things about. So this is the equation we're really working with. So whatever has the symbol that we're working with is the question that we're working on. Oh. That was kind of crazy. All right. Now, if you take a look at step 3, I said make sure that the function that you're working with is only having one variable. Okay, so there only should be one independent variable in my equation. This one has 2, right? It has an L and has a W. Any idea on how to make this have just one variable, Michael?
Make the first equation equal to 1 variable.
Yeah, right. Why don't we work with equation 1 real quick? So equation 1. Okay, 2400 equals 2W plus L. Which one do you want to solve for? Yeah, let's solve for L. I think L is a little bit easier. So we'll subtract 2W on both sides and we'll get 2400 minus 2W equals L. Okay, and then what we can do is we can just substitute that into the area equation. Okay, so area becomes equal to, 2400 minus 2W times W. Okay, and to make this a little bit easier on me in the future, I'm just going to take my W and distribute it between the two factors up front, or the two values up front. So A is really 2400 W minus 2W squared. Okay. So does everyone kind of see how I created one equation that's kind of a combination of the two? Cool. Okay, this is the function that I'm finding the derivative of. Okay, so this is our function. Okay. Now, before we start taking derivatives, what I'm going to do is go to step 4, and we're going to think about what realistic things can this function actually be. Okay, so step 4 thinks is what's the domain of my A function. Okay, so let's think about this. We want to find the domain of A. Okay, and when we think about this, we're thinking about what can I plug into W, right? I'm gonna ask you something. Can W be 5,000?
No,
No, and why not?
because he doesn't have enough sense for that.
Yeah, right. So I'm actually going to write this out. You don't have to, but it makes sense to me when I write it out. Like W can't be 5,000 because there's only 2,400 feet of fencing, right? I know fencing is kind of written. I'll rewrite it. Yeah. Okay, so we can't have we can't work with more fencing than we have, right? Can W be 2,400 then? Because we have 20, no, right? Because there's 2 W's, right? So if W was 2,400, we would have enough for this side of W, but we need another side of W, right? So what do you think the biggest W can be? Sorry, that wasn't a full sentence.
Anything less than 1,200?
1,200, how'd you get 1,200?
2,400?
Have a 2,400, right? So the largest that W can be is really 2,400 over 2 because there's 2 W's, right? And that would be 1,200. Okay, and I know it wouldn't make sense to have W be 1,200 because then like it would be 2 fences with nothing in between. But that is kind of possible, right? So W can be 1,200 and it would make sense. We can't go higher than that though, right? Okay, what do you think the lowest W can be is?
1.
Can be 1, it could be like 0.2. Yeah, 0 is kind of the lowest it can be. It wouldn't really make sense for W to be 0, but it is possible, right? So the lowest it can be is 0. Okay. Okay, so the domain of our function in terms of the question is, so let me write domain is 0 to 1200. And I know it doesn't quite make too much sense to have 0 and 1200 be actual values of W, but this is actually, those are feasible methods. So this is a closed interval, okay? So 0 to 200 is a closed interval of my function. Now I do want to find a max and min. So let's go to step 5. Okay, I've got a closed interval. What method am I using to find the maxes and mins? Well, the closed interval method, right? That kind of gives us a hint. So whenever we have a closed interval that we want to find the max and min of, we're going to the first box here, and we're going to do the whole closed interval method. Okay, so closed interval method. Okay, now this method tells us first to find the critical values. Okay, so we're going to find those. How do we find the critical values again?
Second derivative. X.
Say second derivative or set?
Sorry, first.
First derivative equal to 0. Okay, so first let's find the first derivative. Okay, I guess it's a of W this time, right? So I want to find a prime. What is my first derivative? Yep, negative 4W plus 2400. All right, and all we have to do is set that equal to 0. Okay, solving for W, I guess I gotta subtract 2400. I don't know why I'm writing this out. I guess I'm used to my algebra class right before. So let's do 2400 equals 4W, and then W equals 600. Okay, so yes, I set my derivative equal to 0. I found my W value, and that's my critical value, right? Okay. In my closed interval, I'm going to plug my critical value into which function? The first function, like the original one. So we're going to plug into original function. Okay, so I'm going to do A of 600. Okay, and plugging W into that gives me 2400 times 600 minus 600 squared. Okay, now I'll save you some arithmetic here. You can check me on this, but I'm getting 720,000. Okay. What other numbers am I plugging into A? 1200, right? Because that's an endpoint. Okay, and that would be 2400 times 1200 minus 2 times 1200 squared. Any guesses on what this number is going to be without calculating it?
Yeah.
Actually going to be 0, right? Because 1200 represents like the two widths being 1200 long, but like no length. So this actually becomes 0. Okay, and what do you think A of 0 is going to be? 0. Good. All right. So we're looking for the maximum. We're not really looking for the minimum. You can do that, but the maximum value, okay, is, well, 720,000, right? So that's the absolute max of my function. Is that what the question's asking us for?
No, it's asking for the dimensions.
Yeah, the question's asking us for the dimension. So now we kind of have to step back and actually answer what the question is asking us, okay? So we want to find the dimensions, okay? The max happened when W was 600, so we know what W is, okay? How can I find what the length is when W is 600?
Do the first equation in terms of solving it for L.
Good, so I'm gonna take equation 1, okay? And I'm gonna plug in W equals 600, okay? So I'm gonna go up to equation 1, it says 2400 equals 2 times W, which is 600 plus L, okay? You're gonna solve for L, so 2400 is 2 times 600 is 1200 plus L, and then subtracting off 1200 gives me another 1200. Okay. So I got my L is 1200. The answer to this question is the dimensions of my L and W. So my answer is really when W is 600 and L is 1200. Okay, so that's my final answer here. Yeah.
Why is it 2400?
Is it 20?
Why is that what we're putting in for area?
I'm plugging in.
Different equation. It's together.
Oh, this one? Like, why is this one 2400
No,
in the green? Oh, because I'm plugging it into equation 1, which has 2400 equals 2W plus L.
oh,
Yeah, yeah. I know there's a bunch of equations in these that get kind of messy. All right. Any other questions on this question here? All right. What we're gonna do is if you go to example 2, I put a very similar question. I actually didn't mean to make it that similar, but that's okay. So what I want you to do is go through this example. I want you to show all the steps, okay? So I know this is very similar to this question. You can kind of just figure out what the answer is based on the last example, but why don't you try going through all the steps? I'll give you a few minutes for this and we'll come back in a little bit. Let's use the same L and W dimensions as before. Some of you are still working, that's fine, but I do want to finish this example for the end of class. So let's just go to example 2 and talk about it real quick. This time we just have 400 yards of fencing. I was going to make this a little bit different, but for some reason I don't know. I guess I got kind of lazy when I wrote up this example. So let's just go over it real quick. Drawing our picture, we're going to have the same picture as last time. So I'm actually going to copy this over because I like my picture of Jude in the fence. So we're going to copy that over. Actually, step 1 and 2 are actually the same here, right? So I'm actually going to just copy that over and we'll get him on the fence again. All right. Step 2 is pretty much the same. We're using the same labels for everything. Going up to step number 3, we have the same equation for the area, but our equation 1's a little bit different, right? So equation 1 in this situation was we wanted to take the perimeter of our fence. And I think if I saw this walking around, but we had 400 yards of fencing all around, and that was still equal to 2W plus L, okay, right? Because we had 2W and 1L, okay? Our equation 2 was the same, A equals length times width, okay? And equation 2 isn't written in terms of one variable anymore, right? It has 2 independent variables, L and W. So I think as I was walking around, I saw a lot of you take equation 1 and solve for L. And I think you got L equals 400 minus 2W. Okay, I think you got that from there. Okay, now the function that we want to maximize is the area, right? We want to find the largest area. So we really want to work with equation 2, right? That's the function that we want. So we're going to plug in L into our L in equation number 2. So A becomes equal to 400 minus 2W times W. And multiplying the W over, we get 400W minus, minus 8W squared. Right, that's the function that we want to maximize or minimize. So this is our original function. All right, going on to step 4. Oh my goodness, it's definitely 2W, isn't it? All right, this is, Amy woke up a little bit too late this morning. Yes. All right, I always make some dumb mistake. Dumb but mistake. There we go. Okay, step number 4. Let's think about how high or low W can be here. How big can W be here? half of the max amount of fencing we have, right? So half of 400. So the biggest W can be is 400. So W can only be as big as 400 over 2, which is really 200. Okay, so the domain of my function is between 0 and 200. Okay, and the reason because that is because we have two W's and we want to make sure and W's within those two bounds. Okay, all right, step number 5. We wanted to use the closed interval method, which means first we have to find some critical values, right? Okay, what's the first derivative of my function?
400 minus 4W.
Perfect. And I'm setting that equal to 0. Solving for W, we have negative 4W equals negative 400. So W equals, 100. Okay, that's my critical value. Okay. Now we want to plug stuff in. So I'm going to take my A function. I'm going to plug in 100. I'm going to plug in 0. And I'm going to plug in 200. Okay, so my endpoints and my critical values. I'm not going to kind of bore you with the steps here because we kind of did in the last page. If you did 100, you should have gotten that the area is 20,000. Okay, and then the other two, you should have gotten that the area is equal to 0. Okay. Okay, so well, looks like the maximum one is the W equaling 100 function. So the dimensions of my largest fence are going to be where the W value equals 100 and where the length, well, I guess we have to figure out what the length is, right? So now we got to go to equation 1, plug in 100. So 400 equals 2 times 100 plus L. Okay, and you should get that L equals 200 here. Okay, so the dimensions of my largest fence are where the length is 200 and the width is 100. Okay, any questions on this example here? All righty. When you do these questions, I am looking for all the steps. I know that the fence question is kind of thing. I kind of realized there was something else I could ask with the fence question, but I might leave that to the quiz on Friday, make it a little bit different. But why don't we try example 3? We'll get it set up and then I'll let you go. All right, no questions on the, does anyone have any questions on the fence question? No, all right. Let's go on. Okay, so this is example 3. This is an example of something that you might see on your homework. Sometimes a question is going to ask you to find two numbers, in this case, two positive numbers, whose product is equal to 184. So when I multiply them together, I get 184, and whose sum is a minimum. So I want to minimize what happens when I add the two numbers together. Okay, so let's go through our steps. Step 1, I can't really draw a picture of this. I don't think that's going to help us. So let's actually just jump up to step 2. Okay. We want to find two numbers. So what do you think I should call my numbers? Here's where Jude comes in with his. Yeah, let's do X and Y this time, right? X and Y usually work. They can be our two numbers. What letter should I use for my sum? S, good, that's what I like to hear. So my sum is gonna be S. And what do you think I should use for the product of the two numbers? Don't give me a bad one here. P, there we go. Yeah, here we go. All right, so we have labels for everything, so we know what to do. Let's go to step 3 and come up with some equations for things, okay? So let's do one of our equations. So equation 1. Looking at my question, well, what equation can I come out with the information I'm given?
184 equals X times Y.
Perfect. 184 is X times Y. That's the product of the two numbers. Good. And then what should equation 2 be?
X plus Y equals X.
Of course, x plus y equals s, right? I'm actually gonna write it s equals x plus y because I don't know why, but I am like very particular about how I write stuff. You can write it however you'd like though. Okay, which equation one or equation two, which one am I trying to find the minimum of?
Equation two.
Equation two, right? Because I want to figure out the minimum of the sum. Okay, so this equation is really what I'm working with. Okay, I'm not really working with the 184 thing, but that might be useful information. And equation two is the equation I'm taking the derivative of. Now, unfortunately, I'm at a point where I don't have one variable in my function. So how can I write s in terms of just one variable?
Subtracting X or Y.
If I subtract x or y from my function, it's not going to get rid of one variable, right? I'm still going to have an equation. Like if I subtract x on both sides, it'd just be s minus x equals y, and that doesn't really.
Then put that to the other equation.
Okay, so you're saying do something equation one, right? Oh, you're saying do this. So let me show you what happens when we do this. S minus x equals y.
And we have
Okay.
3 variables. We still have-
Yeah. Then you're just making this equation more complicated, right? So it'd be s minus x times y, and that just makes both equations really complicated. So we definitely don't want to do that. Any other ideas?
Divide one of the variables by one or from one of the.
Yeah, why don't we work with equation one and substitute in equation two rather than the other way around? That might make it a little bit easier for us. So I'm actually going to solve for y here because I like working with x. So 184 over x equals y. Okay, now you can solve for x, but the whole problem, it doesn't really change if you do that. I'm going to plug this into equation number two, and I get that s is equal to x plus 184 over x. Okay, so that's the equation that I really want to find the derivative of. Okay. All right. Yeah, let's keep going. Okay, so remember that another way of writing something over x is x to the negative 1. So let's keep that in mind when we find the derivative. Let's go to step number 4. Okay. What values of x can I plug into this equation?
0 to
Okay, so we all agree that the lowest x can go is 0, right? Because
97.
okay, lowest that x can be, we said 0, and that makes sense because they have to be positive numbers. Okay, you said 97 is the largest that x can be. Any ideas on any higher values of x that x can be?
184, all the way up to 184.
I hear infinity. I hear 184. Let's do 185. Let's say x equals 185. Okay. That's actually not a good one. But I want x times y to equal 184. Okay. Can y be a fraction? Yeah, right. So do you think there actually is a fraction that I can multiply x by if x is 185 to get 184? It would be 184 over 185, right? So there is a fraction I can multiply 185 by to get 184. So is there a largest value of x? No, there actually is no bound for x. There's no highest value for x. And the reason because of this is because y can be a fraction, okay? Y can be as small as a fraction I can make it. So no matter what x is, say x was, I don't know, 1,000, 100,000, y could be 184 over 100,000. And when I multiply them together, I get 184, okay? So no highest value for x. So I don't actually have a closed interval this time, right? I do have a closed bracket for 0, but my outer bound is actually positive infinity. Okay, so there's no highest value for x here.
Well, X can't be 0.
Yeah, X can't be 0.
Oh, yeah, you're true. That is correct. You know what? You are right. Let's put a bracket. Let's put a parentheses. That's a good point. I didn't even realize that when I made this question. Nice job. All right. So this is the lowest x can higher than 0. That makes a little bit more sense, right? Okay. But great. Gotta use Jude's rules here. Greater than 0.
Point it out, that's all.
There we go. We'll draw put Jude there. All right. All right. You know what? I think it's a little bit too late to finish this question, so I'm gonna leave you alone now. I'll let you go, and Jude will be right here waiting.